Okay, so theorem 1. If you start with two different numbers and take their successors, then the successors will be different from one another.
Isn't that kind of obvious?
I think it's pretty obvious, yeah. But we have to prove it. That's what Landau's doing. He's making sure that arithmetic is on a solid foundation that's been proved. So let's take a look at the method of proof. We're going to do it using contrapositive. And with contrapositive, we want to prove if P, then Q. And to do that, we're going to use an alternative method. Which is, if not Q, then not P. And that's the first couple of exercises in your homework, is exploring the structure of contrapositive proofs using Euler diagrams. Okay. So these two are completely equivalent, and when you see an Euler diagram, it'll become really obvious why they're equivalent to each other. So, what we're going to do is we're going to assume for contrapositive that the successors are equal. Then, by axiom 4, we know that x had to equal y. Ta-da! That's the proof. Doesn't look like we've done anything, huh? But let's go and explore this proof a little bit. So assume for a contrapositive that we don't have this, right? Because that's what contrapositive says. It says, suppose that Q is not true, show that P couldn't have been true. Okay? So this is P. Sorry, this is Q, right? Okay? This is Q. And this is P right here. We're trying to show that whenever P is true, then Q has to be true. And an equivalent way to do that is to say, if Q wasn't true, then P couldn't be true. Okay, so these two are equivalent ways to prove things. So what we do is we say, assume for contrapositive that we don't have Q, meaning that this thing is true. Right, this is the same thing as not Q. If not Q, then take a look. We can apply axiom 4 that says whenever two successors are equal, then the predecessors have to be equal. And that's it. We're done, right? We said, if not Q, then by axiom 4, it must be true that not P as well. So we've established that.
So it's just like the negation of it, right?
It's similar. We use negations of the statements. Yeah. Okay. And so the proof itself probably doesn't feel that enlightening, but it's done, right? We now know that if the numbers are not equal, the successors can't be equal, because what this proof basically says, it says, suppose that the successors were equal, then it couldn't have been that these things were different. So the only case that these things can be different is if these things were different to begin with. That's what the proof by contrapositive basically says. The only way you can get two different successors, the only way you can get equal successors is if the predecessors are equal. So what that says is that if they are not equal, it can't be the case that the successors are equal, right? It has to be the case that if they aren't equal, then the successors are also not equal. Okay? So, very slippery type of proof, but once you get it, once you see it, then you see it. Okay. And like I said, the first couple of problems in the homework are going to help to illustrate some of what's going on there. Because I knew it was a slippery idea, so I wanted to give you guys some homework problems to help clarify. Theorem 2. The successor to every number is different from the original. Okay. Remember the systems that we introduced on day 1 where we said 1 succeeds to 2, 2 succeeds to 3, 3 succeeds to 3, and 3 succeeds to 3, and 2 succeeds to 3. What this is saying is that if you have the 5 axioms that we're using, then we can't have that type of behavior. The successor always produces a new number. Okay? Let me write that. Successor to x always produces a different number. So we're going to use proof by induction, and we've been talking about proofs by induction for a couple classes now. You guys will start to like this. It's going to start making sense. So this is a really good example to practice if you're still a little bit weak on induction. So we want to prove that the successor to every number is different from itself, right? And what we're going to do is we're going to let m be the set of all numbers for which that's true. Now, technically at this point, for all we know, m could be empty, right? We don't even know if there's necessarily going to be numbers where the successor differs from the original. So what we're going to do then is we're going to first establish existence, that there's at least one number in m, okay? By axiom, I believe it's axiom 3. Yeah, by axiom 3, x successor is never equal to 1. Therefore, we also have that one successor can never equal 1. Nothing can ever succeed to 1, therefore one successor has to be different from 1. And so what that tells us, it tells us first of all, that's kind of nice. M, meaning the set of all x where that holds, M is not empty. It includes 1. Okay, good. So now that we know that M has something in it, let's pick any element from M that we want. Any element in M that you want. M is the set of numbers where the successor is different from the original. So by definition of M, that says pick up any x in there, and you know its successor is going to be different from the original. And we'll do. Let's take these two values, which we know are different from each other, and let's consider their successors. Okay? By theorem 1, what do we have? We have that if you have two different numbers, then when you take their successors have to remain different. And so what does that say? It says the successor to x is also one of the items whose successor is different from the original. So the successor to x is in M. And so what have we concluded? We've concluded that 1 is in M. And all successors are also in M. So what is that telling us? Well, first of all, 1 is in there, right? 1 has the property that the successor is different from itself. And the successor to 1 is in there too. So we know that 2 has the property that the successor to 2 is different from 2, right? And the successor to that is in there. So 3 has the property that the successor is different from 3. And the successor to that is in there. So 4 is in there. So 5 is in there. So 6 is in there. So as long as 1 is in there, and as long as all successors are in there, then M has all the natural numbers. So every natural number that you pick up has the property that the successor is different from the original. All right, so by axiom 5, which is the axiom of induction, all naturals satisfy the property that the successor is different from the original. So this is a very, very clean proof where you can practice proofs by induction, and there's very few extra details to get hung up on. It's very clean and easy to understand. So if you're a little bit hung up on induction still, how many people are starting to come around? Feel like induction's sort of making more sense? So a lot of people are still kind of not real happy with it. So this is a good proof to study then, right?
So this is all theorem 2.
Yep, this is theorem 2. So here's some theorem, and then here's some
1 and all the natural numbers successors are in.
Yep, exactly. For all natural numbers, the successor has to be different from the original, right? And how do you do it? You say, well, let M be the set of all items for which that holds. And for all we know, M could be empty, right? So what do? We say, okay, let's let M be the set where this condition holds. Then let's go ahead and just verify and see if 1 is in there. How do we know that 1 is in there? Because axiom 3 tells us that nothing succeeds to 1. So boom, M has 1 in there, right? Now that we know that 1 is in there, let's prove that successors are in there. Okay, so here we proved that all successors are also in M. But now if 1 is in there, and the successor to 1 is in there, then that means 2 is in there. If 2 is in there, that means 3 is in there. If 3 is in there, that means 4 is in there. So what that says is that M contains all natural numbers. So every natural number then has the property that the successor is different from the original. Yeah. It'll start to feel natural. It won't just start to make sense. It'll start to feel like common sense. It'll just start feeling natural.
So you know how you said to pretend that you don't know how it works. So this is just basically the rules of counting. 1, 2, 3, 4, 5.
Yep, exactly. It's saying that when you count,
you can't count 3, 3, 4, 5, 6, 7, 7, 8.
Exactly. Yeah. When you count, you're always going to move to the next one.
Yeah.
So we just constructed that property from the axiom. Exactly. Okay. All right, good. So that's theorem 2, and that's the first proof by induction that Landau does. Okay, we did a couple in class, of course. But now we can see a Landau style. Okay. So here's theorem 3. Who wants to summarize what this is telling us? Yeah.
X can't be 1, but it could be some other number. However, the other number cannot equal X.
No, it's telling us something different from that. I think I can see where you're going with that, but yeah, it's telling us something different.
So you used a 0?
No, we don't have a 0. Remember that 1 is our starting point. But I kind of like how you're thinking. I can see where you're going with that. So talk it out a little bit, see if you can get started in the right place.
It's the next number in the counting system.
Okay, that's involved in what this theorem is telling us.
Does U successor just represent every number after 1?
Not quite every number after 1. Oh, U successor, yes. U successor could be any number after 1. Yeah.
So like the halfway point?
No, not a halfway point. Let's try some specific numbers. Suppose x is 9. Then what is u?
10.
Uh-huh.
8? Okay.
Oh, wait,
What?
if
If x is 9,
9.
u is the thing that succeeds to 9, so u is
It's 8.
8, right? So what is this saying? It's saying, okay, suppose that we add 27, then what is u?
26.
26. What if we add 30, now let's do 178, then what's u?
Oh, so it's just 2 before.
177. So yeah, well, it's 1 before, right? So what this says, it
But
says,
U is.
as long as you're different from 1, then there's something that succeeds to you, right? So not you, the letter,
Yeah.
you, the number. Okay, this is all bad. So as long as you're different from 1, as long as a number is different from 1, then there's a number that succeeds to it. That's all that this theorem says. As long as a number is different from 1, take 11 for example, then there's a number that succeeds to it. What is it?
10.
10. As long as a number is different from 1, there's a number that succeeds to it. What about 94? 93 succeeds to it. Okay, so that's all this theorem says. If you're different from 1, then there's a number that succeeds.
So there's always a number before a number.
Yep, that's all the theorem says. There's always a number before a number, unless you're at 1, because 1 is your starting point. It seems like half the class is enjoying it and half the class is like,
I mean, it's
Get out
just
of
like,
here.
oh, these are just the rules of counting.
yeah, we're just counting.
But
We're
it
just
makes it
counting.
sound complicated when we already know it. You know?
All right, so let's take a look at the justification. It seems obvious, but we have to make sure math is on a solid foundation, so we have to prove it, right? Whenever I say number, we're just going to assume I mean natural numbers, right? We're not talking about fractions or anything, so whenever I say number, we're just talking about naturals here. So we're going to let n be the set of all natural numbers that have a unique predecessor. Now, just a reminder, we don't know anything about the natural numbers. And so for all we know, this set could be empty. Okay? And we're essentially going to prove that not only is it not empty, it's in fact all natural numbers except for 1. Okay. So for all we know, this could be empty. But what we're going to do is we're going to define m to be the set n together with 1. So we're going to use induction again. then just by the way we constructed this set M, we know that 1 is a So now, let's pick up any item in M different from 1. Could be 2, could be 3, could be, we don't really know what element we're picking up. We just want to make sure that it's different from 1. Now you may ask, how do we know that we can pick up something different from 1? The answer to that is, well, note that one successor is in M, right? Because one successor is an element that has a predecessor.
Isn't there no successor to 1?
Well, we're not looking at 1, we're looking at one successor. Right? This is the number 1 successor, it's not the number 1. That's not 1, it's one successor, and take a look, that number has a predecessor. It's called 1, right? So this guy right here is guaranteeing that we can pick up a number from M that's different from 1, okay? I'm going to write this in 2 lines here. Since X is in M, and since X is different from 1, we have that X is equal to the successor of some number U.
That in like real life counting situations.
Yeah, real life. So this says here that, well, it mainly goes back to the definition of M. Someone remind me, what is M in this problem?
Set of all natural numbers.
That's what we want to prove. It will turn out that M is all naturals, but for now, we just have to use the definition of M that we started with. M. So here's M. And it says, give me all the natural numbers that have a predecessor, and we'll toss 1 in there as well. Okay. So this next line says, okay, pick up an element that's different from 1. How do you know that you can do that? Well, because one successor definitely has a predecessor, and one successor is different from 1. So we know there's at least one thing in M that's different from 1, right? So whatever thing you pick up, just make sure it's not 1. But since we're pulling it out of M, what is M? M is the set of all numbers that have a predecessor. Okay, so that's what this says. It says, pick up a number that has a predecessor. Then u successor is x, right?
All right, you're gonna have to do that piece over again.
Okay. Yeah, some people
say
some-
like,
I'm confused.
and it's like 2, then 1.
Yeah, exactly. It's like, okay, we know that 1 can't have a predecessor. That's axiom 3. That says, throw that out the window. 1 is our starting point forever, right? So 1 can't have a predecessor. But what we're going to do is we're going to set m to be the set of all numbers that do have a predecessor, with 1 thrown in there, right? These are all the numbers that do have a predecessor, and we're going to toss 1 in there, okay? For the purposes of this proof, though, we kind of don't really care about 1. We care about all the other numbers. So what we're going to do, we're going to pick up a number in m, and we want to make sure that we didn't pick up 1, okay? The question is, how do we know that we can even do that? Because, take a look, 1 successor is an element of m, right? Because it has a predecessor of 1. So we know that in m, there is something different from 1 that we can pick up. And so we say, all right, we know that we can pick up something different from 1. And so now that we know we picked something up, let's go ahead and label it using the successor notation. X has a successor, or sorry, X has a predecessor, so we'll label it as the successor of u. And we know we can do that because we know there's something in m aside from 1. So whatever that is, we picked it up. Okay. So this guy has a predecessor called u. So when you take the successor, you get x, right? So now, let's go ahead and take the successor. X successor is different from x. How do we know that?
Because x successor is whatever x. Okay, so say that x is 5. The x successor has to be 4. It can't be 5.
You're
It
saying
can't be
that
the same number.
yeah, the successor has to be different
Yeah.
from the thing you started with, right? So that has a name. That's called theorem 2. Theorem 2. Yep, theorem 2.
No number, every number is different.
Yep, every number's successor is different from the original. So when we take x successor, we know it's different from x by theorem 2. And that's it, basically. Right? We know 1 is in M by definition of M. And here we said, pick up any other element of M. Then the successor is definitely going to be in M because the successor has a unique predecessor. It's called X. Right? And so what have we shown? We've shown that 1 is in M, and also all successors are in M. And so if 1 is in there, that guarantees 2 is in there. 2 is in M, that guarantees 3 is in M. And so just kind of like you're knocking down a chain of dominoes, if 1 is in there, then 2 is, then 3 is, then 4 is. And so M has to be all naturals, right? basically by axiom 5.
When you're proving by induction on our own, it's not always clear what we can assume and what we can't assume.
It's very, that definitely gets difficult.
So,
So what you need to do is you need to very clearly define what you mean when you say M. That M that we keep using in these proofs by induction, that's the really critical piece. M, in this case, in this one's a little bit confusing because we had to rig it kind of funny, right? But what is M for the most part here? M is the things that have a predecessor. Now we had to throw one in there for technical reasons, but you basically want to think of M as take all the numbers that have a predecessor. That's M, right?
For all m's or just for this case?
Just for this case, yeah. M changes every time you do a proof by induction, okay? But whatever the case, you're defining M to have a very specific definition, okay? In this particular problem, it's the set of all things that have a predecessor. And we had to throw one in there for technical reasons. Now, what you do is, for proof by induction, you need to verify that one is in M. And that's why we had to throw it in, is because one doesn't have a predecessor. So we said, let's take the things that do have a predecessor and toss one in there with it, because it would feel lonely otherwise, okay? Yeah, 1 is the loneliest number, the loneliest number I've ever seen. So the main thing we care about is, let's consider the set N, right? 1's in there, which we needed for induction. But the main thing we care about is, let's choose a number in M that's different from 1. And we know we can do that because one successor is definitely in there. And so one successor has a predecessor. And so we know we can pick up something from M that's different from 1. Then here, we're saying, now that we have this thing from M, let's look at its successor. So what do? You look at what that means in this problem. You say, what does M mean? It means that you have a predecessor. Okay. So every single time you do a proof by induction, you have to clearly define M. And then when you pick up a random element from M, the property that element has is the property that you find M to have. Okay, so that is what theorem. I think now's a good time to take a little break. Any questions before we leave for break? Let's look at the theorems that we've proved so far. Theorem 1. If two numbers are different to start with, they stay different when you take the successor. Common sense, right? If 5 is different from 7, then 6 will be different from 8. That's all that's saying, right? Theorem 2. The successor can never equal itself. Right? The successor to a number can never equal the original. So we can't have that behavior 1, 2, 3, 3, 3, 3. You always have to keep changing, right? 1, 2, 3, 4, 5. And the next theorem, all that we did is we said, suppose that you're different from 1, then there had to be something where you came from. If you're 9, you came from 8. If you're 27, you came from 26.
It's like every number had a parent.
Yeah, every number had a predecessor. So everyone's clear, at least on the statement of the theorem side. Good. All right, so yeah, we'll take a little break, 10-minute break. Ask me questions if you have any. And this is this is where I told you you guys were going to start crying. I have some comments that I want to
Just super sad.
talk about before we move on to talk about addition property. You can get the screen.
For what?
I'm saying for the video, you can get the screen.
Sorry about that.
Do not pay your bills without really work.
It's a scam.
Is this
All
kid?
we only for budgeted 31 classes in the semester, so yeah, there.
Okay, this is the one I want. This is a relatively well-known book, and a lot of people work through it for their own benefit. And this is in the preface to the teacher. Do you remember that it says not to read the preface for the teacher? This is part of what's in there. How many people have read it? Out of curiosity?
I did.
Couple. Yeah, so this is part of what's in the preface to the teacher. So Peano, whose arithmetic we're developing here, Peano defines x plus y for fixed x and all y as follows. X plus 1 equals x successor, and x plus y successor is the successor of x plus y. And he and his successors then think that x plus y is defined generally, for the set of y's for which it is defined contains 1, and contains y prime and contains y. But x plus y has not been defined. All would be well if, and this is not done in Peano's method because order is introduced only after addition, one had the concept of numbers less than or equal to y and could speak of the set of y's for which there is an f of z, defined for z less than y with the properties given here. I didn't expect you to understand that because
Yes, it's just words.
it's the preface for the teacher. This guy responds to this guy's question, and he's saying, oh, well, you need to think of it this way, right? And this person's responding to this guy's question, saying, oh, yeah, you should think of it this way. What I'm trying to get across here is that the proof that we're about to work through is extremely subtle. Okay. The people who post on this board, they're obviously very sophisticated, and they have a lot of background. And I just wanted to share this personal story with you that the last time I taught this class, I got stuck on this proof. And these are some notes that I made to myself. I've got notes up here, I've got certain underlining, I've got notes. I got stuck. And I basically had to leave it there and I couldn't figure out what was going on in this proof. But I don't feel very bad about that. As you'll notice in those things that I was just now showing you, a lot of people get stuck here. Okay? And I just want to show you this absolutely hilarious quote from the Landau's teaching to the, preface for the teacher. He says here, with the help of my colleague, John von Neumann in Princeton, I had worked out such a procedure based on a previous introduction of ordering for this book. This would have been somewhat inconvenient for the reader. At the last minute, however, I was informed of a much simpler proof by Dr. Palmer. And the thing that I find funny about this is that he's getting stuck on addition. He's getting stuck on properly defining addition. And he had to consult with one of the greatest mathematicians of the 20th century. This is John von Neumann here. Literally just a hugely important mathematician. And he's like, dude, help me out here. I can't figure out this addition thing. And I can't even imagine what von Neumann must have thought. Like, adding what? Some screwed up, crazy math thing? And Landau's like, no, I'm just trying to add. I'm just trying to figure out how to add. So, frankly, there's stuff going on, like with this stuff here, that f of 1 equals x, f of z, successor equals all that stuff, that I still need to sit down and work through to figure out exactly what some of these subtle things are that are going on in the background that I'm not picking up on, but I do now at least understand this proof. As you can see, I've spent many hours dissecting this, and I've got it figured out. And it is accessible to you guys. It's not going to be easy, but if you work through this, then you'll know how to add. So, that x plus y would be, yeah, x plus y successor is x plus the successor of y. So let me give you guys the first big red flag that's going to help you out. This is not the definition of addition.
Yeah, that makes sense.
These are properties that addition must satisfy, okay? So this causes a lot of confusion. That little blurb that I was showing you from online, that's only one of many where people get hung up on exactly how Landau's work in this. This is not the definition. These are properties that addition must satisfy. Okay, so that's kind of like saying, it's kind of like saying this. Think of an object made out of metal that flies above the earth.
Satellites.
I'm so glad you said that, because that's exactly one of the things I was thinking of. You could say plane. You could say space shuttle. You could say satellites. There's all kinds of different things that are made of metal that fly above the earth. Everyone see that? So just by listing off properties that you want, that's not the same thing as defining what you're talking about. Because you could say, the other way around, you could say, a plane is a metal thing that flies above the earth. There you defined it, and then you listed the properties that it has. Landau hasn't done that here. He just said, hey, we're going to define something in a little while, and this is what we're going to require that it satisfies. So it's like we're saying, hey, later on we're going to talk about a thing that's metal and it flies over the earth. But we haven't actually said what we're talking about, right? So that's what Landau's done. He said, these are things that it's going to do. We just don't know what it is. Okay? All right, so this is not the definition. It's only properties that it satisfies. And this is still the statement of the theorem. Furthermore, the definition of addition so Landau has so far told us, hey, we're going to introduce this thing. Haven't told you what it is yet, but that's what it's going to do. And he says, and also, the thing that follows those rules, there's only going to be one way to introduce addition where those rules will be satisfied. Okay? So we're going to prove uniqueness first. Now, we're actually going to work through two proofs of uniqueness because Landau's proof uses some notation that's kind of hard to interpret. So what I'm going to do is I'm going to work through Landau's proof using his notation so that if you're reading the book, you can make sense of what he's saying. But after I prove it using his notation, I'm going to switch notations to something different that will hopefully make it a little more clear. Okay? So Landau denotes the addition x plus y, denotes that operation as a sub y or b sub y. And we're going to use both of these. Because what we're going to do is, we don't even know if there's a unique way to define addition. Right? That's like saying, could 5 plus 7 equal 12? And also, could 5 plus 7 equal 15? We don't even know if the addition operation is necessarily going to be unique, right? So we're going to define two ways of adding. There's adding x plus y using this technique, and there's adding x plus y using this technique. And for all we know, these could be different. What we're going to show is that as long as you satisfy these two properties, then these two are exactly the same. They're not different from each other. Okay? So just starting out, they may be different, but we're going to say if they satisfy that, we'll find that they have to be the same. So 5 plus 7 will always be 12. 5 plus 7 can't also be 15. Okay? Okay. So we're going to do proof by induction. And whenever you do that, you define this set M. And so you have to be real careful about how you define it. M is the set of all y such that the two different types of addition agree with each other.
Wait, with y?
Y is just a random natural number.
And so in this case, the A with the Y, the subnote Y is X, and that other one is Y, or no?
So A sub y represents x plus y using one form of addition.
Oh,
And B sub y represents x plus y using another form of addition that is possibly different.
okay, so this is X plus Y equals X plus Y.
Yeah, it's x plus y equals x plus y, where you have possibly two different definitions for addition.
Okay.
Okay? And that's why we're using A and B here. It's like method of addition 1, method of addition 2. For all we know, they could be different.
Well,
So
we mean possibly. There's only one way, or there could be two ways.
Is
there,
that
Like,
there could be
there's
two
not,
ways.
there's not always two ways?
No, we want to show that as long as you satisfy those two properties, there's only one way to define addition. And that's what we want, right?
so he uses the two, for example, like if he says 5 plus 4 is 9, or 4 plus 5 is 9. That's
Yeah, he's
two
not
ways.
talking about that. He's saying, think of it like this. Think of it like this. A sub y, and this is how we're going to prove it later on. A sub y is x plus y with a little 1 right in there.
What's that mean?
And that means the first type of addition. For all we know, there could be two different ways to add numbers. Okay? And so the first type of addition says add x and y using the first method of addition. Okay? By, on the other hand, says add x and y using the second type of addition. And for all we know, they could be different, right?
Or it could be the same?
And it's going to turn out that as long as they satisfy these two properties, it's guaranteed that they'll be the same. So you'll have unique addition.
But those two properties aren't necessarily the same as that A, Y, B. They're the same.
Correct, yeah. So these are just two ways to add that satisfy these two rules.
So that meant they just happen to be labeled A and B, but they aren't the same A and B as that A and B.
Oh, yeah, I see what you mean. Yeah, let's call this
like almost like the
capital A
yeah.
and capital, yeah, I see what you're saying.
Yeah.
Okay, so these are two different ways to add numbers. AY says add x and y using the first method, and BY says add x and y using the second method of addition. So here we go. M is going to be defined to be all the y, all the natural numbers y, such that the two methods of addition happen to agree with one another. And for all we know, maybe that never happens. Maybe we have two different types of addition where when you add numbers, you never get the same result. So theoretically, M could be empty, where there's no numbers that make these two equal. But we're going to prove that no, actually it's not empty. M will include 1.
But we already know that because the has that's
Well, we don't know that actually, because how are these two different methods of addition even defined? We haven't even defined
This
it.
is a brand new,
Yeah, these operations have appeared out of nowhere, and we don't even know how they're defined. What we're going to do is, even though we don't know how they're defined, we can at least still work with their properties. Okay? So, we can show that whenever y is 1, we have that a sub 1 is equal to b sub 1. What that means is that x plus 1, using the first method of addition, has to equal x plus 1 using the second method of addition. Okay. So we need to prove this. property A states that whenever you have x plus 1 equal to x successor, whenever you have x plus 1, and that's what this means, it has to equal x successor. And property B, so property A, property A also guarantees that whatever you defined the operation B as, that also has to equal x successor. You have method of addition 1. But if it satisfies those properties over there, then that guarantees that x plus 1 using the first method still has to give you successor to x. This guy here says, suppose you've got addition using a second method, b. This says x plus 1 also, x plus 1 using the second method also has to give you x successor.
So you mean like the big B, big A?
No. These are the lowercase a, lowercase b, meaning the different methods of adding. So what we have then is x plus 1 using the first method gives you x successor. X plus 1 using the second method gives you x successor. Therefore, no matter which method you use, x plus 1 with the first method or x plus 1 with the second method, you get the same answer. Therefore, x plus 1 using the first method is exactly the same as x plus 1 using the second method. So when y is equal to 1, the two methods of addition have to be the same.
Can you give us like an example of both methods using natural numbers we know right now?
I kind of can't because they're going to turn out to be the same.
Yeah, that's what.
And so I think the most confusing thing about this is the notation, the A and the B notation.
Yeah.
And so the only reason I'm going through this proof is because this is the one that's shown in Landau. I'm going to change notations and we're literally going to redo this exact same proof after we finish this. This is just so that when you're reading Landau, you can refer back to this, okay? When we switch to that new notation, it's probably going to be a lot more clear, okay? Okay, so there we go. We've got that whenever y is 1, that any method of addition that you want to define, it has to give you the same result. X plus 1 is always going to be x successor, okay? So in other words, we've demonstrated that 1 is in M. So now let y be any element in M, which we know there's at least 1 in there, right? Yeah. Because we proved 1 satisfies it. Someone remind me, what is M? That's what we're trying to prove.
Well, it's natural numbers that have a successor.
No. We want to prove that successors are in there. It is a set. Good, we'll start there.
It's a set that may or may not contain natural numbers.
That's right.
It's a set of y.
It's the set where the two methods of addition agree with each other.
But there's,
You have to make sure that you keep the definition of M in mind at all times, because this goes back to Monica's question about when you're doing a proof by induction, it's hard to know what you can assume and what you have to prove. You can assume whatever you assumed about m. We said set m to be all the y values where the two methods of addition agree with each other. And we know that there's at least one item in there because we took a look at one. We said, well, the successor, x plus 1 has to be the successor of x using the first method, and x plus 1 has to be the successor of x using the second method of addition. Therefore, they're the same. And so the y value 1 is in m, because in m, those methods of addition agree with each other.
Why would there only be two methods, two possible methods? Wouldn't there be a bunch of different possible methods if there were methods in question?
We're actually going to prove that there's only one.
Oh.
So why aren't there more? It's because we're proving that if you have these two restrictions that you have to follow, then there can only be one way. We're proving that right now.
Oh.
Okay.
So we're going to do things so many wrong ways, prove that there's only one right way. It's like, why do we have to prove there's only one way?
Well, because we don't know that there's only one way. I mean, let me ask you this. Do you want to live in a world where you don't even know that addition is unique? Do you want to live in a world where 7 plus 5 could be 12, or 7 plus 5 could be 15?
It all depends on how you define it. People define hundreds of
Well,
Well,
what the possibilities of that would be.
I mean, it could be code.
I mean,
Crazy world.
let me see. So let me see if I am getting your idea straight. You're saying just define it to be unique? Or is that
I don't know, I'm just confused now.
Yeah.
I feel like you're making
There's
something
so
so
many
simple
possibilities.
complicated.
Yeah.
Well, it is complicated, just
And
like I
then
was saying
you
earlier
keep
about
saying
Johnny
that
Bunker.
M is okay in this particular situation,
Uh-huh.
that this is what M represents, but in another situation, that's not what M represents.
Yeah, but I already know, it's like
So we don't really know what the hell M represents.
No, I know, it's M. You have to be very, very
We're all
careful
getting mad
with
at you.
M. I know, you have to be very,
It's very
careful.
frustrating.
It is. Look, I showed you my notes on this very
you
proof.
keep asking
I mean,
what M is, but it's like,
this
So
part.
we don't know what, there's no logical
There's M.
explanation for that.
There's M. It's the set of numbers where the two methods of addition agree with each other. You define M at the very beginning. You say, okay, I need to define M. So what did we do? We defined M to be the set of numbers where the two methods of addition agree with each other.
Okay, so M is the chocolate chip cookie with walnuts in it. So there's an equal amount of chips as there is walnut pieces inside of the cookie, which is M. Correct.
Interesting.
It's something I can relate to.
Yeah, right. I know, it's crazy abstract.
I
know.
need an example.
Yeah, let me think. Yeah. I mean, your analogy is probably safe to
Okay,
think about.
thank you.
Yeah. So if you want to think that way,
I do.
and so let me get this straight. If you're adding walnuts or if you're adding almonds, it doesn't matter.
No,
The arithmetic is
just
the same,
nuts
basically.
and some kind of candy chip, but they're all inside of M, but there are equal amounts of them in M. And also the M could be any kind of cookie. It could be a sugar cookie, it could be a different kind of cookie, but there
I
are
think it's
equal
better
amounts
than-
of nuts and chips.
what happens?
Yeah, let's stick with nuts and
one
chips.
way.
Okay.
Okay.
Well, I mean, because your M represents different things.
Oh, okay. So you're
Your
saying
set
from
of
proof
M.
to proof to proof.
Yes.
Yeah,
M
it changes
changes.
proof to proof. That's right.
Yeah.
But every proof that you're looking at, you have to define M to have some very, very specific properties. Okay. So what did we do in theorem 2?
Say every number is different, right?
Say that again.
Like every number is different from the next number. There's like, there's no same number.
Well, we need to use that eventually. I think you're getting at induction, right?
Yeah.
Yeah, we need to use that eventually. But that's something that we have to prove along the way, that it works for X and it works for X successor. And that's what you're talking about, right?
Yeah.
And that eventually you're going to hit everything. Because if you can hit all the successors, you'll hit everything, right? Yeah, and so that's something that you use, but you have to sort of prove it along the way. But let's go back through these proofs and let's just take a look at how they set up M. So theorem 2, we used induction. So we said, consider the successor to a number. We want to verify that you never land back at the same number when you succeed, right? So what did we do? We said, okay, let M be the set of all numbers for which this holds true, meaning let M be the set of all numbers that satisfy that.
In that particular case.
In this theorem, yeah, in this proof, we're going to let M be the set of numbers where that condition holds. So we have a very, very clear, precise definition of what M is for this proof. It's the set of numbers where that condition holds.
What is the equals with the line through it symbol?
Not equal.
Does not.
That does not equal, okay, so it's the same as the slash.
Exactly.
Okay.
Okay, so we have M very carefully defined. And what do? We said, well, is 1 in there? Yeah, 1 is in there because 1 can't succeed to itself by axiom 3. Now, pick up any element in M. When you succeed, you have to land at a different number. Well, what does that mean to pick up an element in M? It means that that condition holds, because that was the definition of M. So if you pick up an element of M, guess what? That has to be true, that the successor is different from the number. Now we use that property that that element has, and we say, now that I know this is true for that element that I picked up, let's prove that it also holds for the successor. That's true by theorem 1. So if it holds for 1, and if it holds for all successors, then this condition holds for all natural numbers. M is all natural numbers because 1 is an M. And if 1 is an M, then 2 is an M. And if 2 is an M, then 3 is an M. So M changes every time you do a proof by induction. But you just very, very carefully define M to have a certain property. In this case, M was the set of numbers where that condition held. And when you define M, you don't even know if such numbers exist. And so part of your job says, okay, let's go and just see, is 1 even a number where that holds? And so there we go. 1 turns out to be an M. And so now we know that M is not empty. There's at least one thing where that condition holds, right? Now that you've done that, you pick up any element from M that you want. And you prove that it also holds for the successor to that element. So now, since 1 is in there, and you've proved it for all successors, that guarantees that 2 is in there.
Okay, so when you have like the x and the parentheses with the successor, and then the successor, do those like cancel each other out? Or is this the successor of that successor?
It's the successor to that successor. Yeah. So 1.
So you do the successor inside and then that
So
successor.
successor
Exactly, yeah. So what would 1 successor be?
3.
3. Exactly, right? 5 successor.
7.
7, right? You just
Okay.
successor once to 6, and then successor again to 7, right? Okay.
To that successors.
All right. So here we're back talking about addition, and we're just having a little fun. Think of it as having fun, okay? Where we're saying, hey, you know what? Wouldn't it be fun if we could define 5 plus 7 to be 12, and also define 5 plus 7 to be 15? What a crazy world we'd live in.
No, we can't.
So what we're proving here is that no, we don't get to do that. Anytime you define addition that satisfies those two properties, it's guaranteed that the additions have to be the same.
The battery's running low.
Yeah, we're almost done with class. So, of course, we're in the really important part right here. But anyway, let's go and continue while we're here.
Should I pause it?
No, we'll keep going, and I'll just do it really quick. Okay, so what have we done? We said let's let AY be one type of addition, BY be another type of addition. We said let M be the set where they agree. For all we know, maybe there's nothing else, right?
Does it mean, oh, as in Y being, AY being a certain type of addition and PY being a certain type of addition as, not the properties, but
Yeah.
Like an A1 and B1? You can do this A1 and B1?
Like +1 and +2, where we have +1 is like the first type of addition, +2 is like the other type of addition. Right.
So is it the same as the A1 equals B1, as in the different types, but they're the same in that? I feel like they're almost the
Well,
same.
yeah, so we're saying that these could be different types of addition, but at least when y is 1, they have to agree.
Oh, okay, so they're saying so that M is a set of y, and then such that, so any number, as long as that y is the same number, is going to be equal, or that y could be a different number?
Well, all that we've done is we've proved it for y equal to 1. Whenever you have x plus y with y equal to 1.
And then last thing about this, so ay equals by means that, say, the y means it's the same, meaning if y were 3, it'd be a3 equals b3?
Yes.
Okay, and so, but it wouldn't be a3, and then the other y couldn't be like 10.
Correct.
Okay,
So
okay,
it's the
cool.
same way. Okay. All right, good. So let's take a look at, we've proved that if you have two different types of addition, they at least have to agree when you're adding 1. Okay. Now, suppose that you add any other number. So let me just remind you what AY represents. AY type of addition plus 2 is like the other type of addition. Right.
So is it the same as the a1 equals b1, as in the different types, but they're the same in that? I feel like they're almost the
Well,
same.
yeah, so we're saying that these could be different types of addition, but at least when y is 1, they have to agree.
Oh, okay, so they're saying so that M is a set of y, and then such that, so any number, as long as that y is the same number, is going to be equal, or that y could be a different number?
Well, all that we've done is we've proved it for y equal to 1. Whenever you have x plus y with y equal to 1.
And then the last thing about this, so ay equals by means that, say, if the y means it's the same, meaning if y were 3, it'd be a3 equals b3?
Yes.
Okay, and so, but it wouldn't be a3, and then the other y couldn't be like 10.
Correct.
Okay,
So
okay,
it's
cool.
the same way. Okay. All right, good. So let's take a look at, we've proved that if you have two different types of addition, they at least have to agree when you're adding 1. Okay. Now, suppose that you add any other number. So let me just remind you what AY represents. AY represents x plus y, where we have the first type of addition. Okay. So let's go and let AY equal to BY. Why do we know that we can do this?
Because a1 equal b1.
No, we're proving that there's one way to do it. Why do we know that we can even do this? Because we're choosing y to be an m. What is m? M is the set of all y's such that these agree, right? So since we chose y to be an m, then it satisfies that property that the two types of addition agree. You got it? Okay. Now let's consider y successive. And the first type of addition, which we're calling A, satisfies this property here. Which is that whatever addition you've defined, we have that when you take the successor to the sum, you get the sum of x plus the successor to y. So here versus here?
Yeah.
So here, what we're doing is we're adding first and we're taking the successor of what we got.
Oh.
Yeah, so something like if you have 5 plus 9 is 14, you can do 5 plus 9 is 14 and then take the successor, all of 15, right? And then this says that has to be the same as take the successor to 9,
So we have like 9.
which is 10. That has to agree with 5 plus 10. Is 5 plus 10 15? Yes. And we see that 5 plus 9 successor is also 15.
Oh.
Right. So this says add first, take the successor. That has to be same as taking the successor of y and then adding those.
And they should be the same.
And that's what this property requires, right? We're going to require that property be whole. So we're requiring that always whole. Okay. Then what does this say using our A and B notation? What that says is that, remember that A sub y just means x plus y, where it's the first type of addition. So this says take x plus y and take its successor, and this says take x plus y and take its successor. Then what this property means in terms of this A notation is that AY successor has to be AY successor, where this is all inside the subscript. So these two equations are meant to be the same thing. So if you add x and y first and then take the successor, you get the same thing as adding x and the successor of y. And with B notation, what does that mean? It says by, which says take x plus y using the second type of addition. Successor has to be b y successor. Again, same equation, it's just one is written using that stupid b notation that he uses, and the other is written using a plus.
They seem to be identical. So why are we using it if they're the same?
They're not necessarily the same. The thing that makes them not necessarily identical is that we could have two different types of addition, right? We could have type of addition 1, and that corresponds to the A addition, or we could have type of addition number 2, and that corresponds to the B addition. Right? That's what I keep saying about, for all we know, in this system that we're constructing, for all we know, maybe 5 plus 7 is 12, and there's another addition where 5 plus 7 could be 15.
We just haven't done that yet.
Yeah, we just need to verify that that can't happen. And so we've got these two different types of addition. Remember, AY just means x plus y. And BY just means x plus y. But it's two possibly different ways to add. And what we've done so far is we've verified that for y equals 1, they're the same. Now we need to verify for all the other numbers that AY and BY are always the same. Okay. So let me just finish this up real quick because we are close. What we're going to do is recall. We're going to note that AY is equal to BY by assumption. Right. So let Y be an enemy. What does that mean? It means that this is a point where the two types of addition agree. Since we know we're looking at this item here, where the additions are known to agree, let's use that and we'll take successors of it. So on the left, we get a y successor. That has to equal ey successor. But we're requiring that this property hold. For whatever addition we define, we're requiring that this property has to hold. And so we saw that using this A and B notation, we can rewrite this thing like that, and we can rewrite this thing like that. Right? We're literally just replacing this with an equivalent way to write it. This thing here, since it satisfies that relation, has to be able to be written in this way. And this thing here, since it satisfies that relation, can be written in that way. So if this is true, then we know that's true. But now what have we shown? We've shown that the successor to y is also in M. If y is a point where the two types of addition agree, then the successor to y is another point where the two types of addition agree. Okay. And so we have this, since 1 is in M, and all successors are in M, M is all natural numbers. I mean, that's what we were trying to tell you when you're asking. Yeah, I agree. It's pretty obvious, in the least obvious way possible. But yeah, we've proved that we want our addition to satisfy these two properties. For all we know, there could be two different types of addition that satisfy these. So what are we doing? We want to verify that there aren't multiple different ways to define addition. As long as you have these two properties, there's only one way to add numbers. Okay. So let me just look through the homework real quick. Yeah, you guys are going to be fine. This is